So our next big topic in chemistry is solutions. I'm going to start out by talking about what solutions are and why they're important to us as chemists and as people, and then how can we understand them. So how can we create solutions at a certain concentration? How can we dilute solutions to a specific concentration? And how can we understand what's inside of a solution if we have one that's already made? So we can start to understand where solutions fit if we draw a flowchart to represent different types of matter. So depending on whether or not we can physically separate a substance from other substances, a sample of matter can be classified as either a pure substance or a mixture. So a mixture is made up of more than one part, obviously, and at the fundamental smallest level, a pure substance has particles that all look the same. They don't all have to be the same element. They can be, and if they are all the same element, then that's the thing that I'm looking at. And so I could have some pure copper, for example, or I could have some pure oxygen, or I could have some pure mercury. All of those things would be pure substances and they would be pure elements. But I can also have compounds. Those also count as pure substances because if I break them down to their smallest particle, they would all be the same. So for example, water. It's made up of hydrogen and oxygen. They're not all the same atom, but a water comes as a discrete unit. If I break down a sample of water, I will break it down to its smallest unit, which will be H2O molecules. And I can't break it down any further without doing a chemical reaction. So it's a pure substance, it's a compound. Ionic compounds would fit into this category as well. So if I have some sodium chloride, table salt, that would be a pure substance, but it's a compound. So ionic and molecular compounds would fit here. Now on the mixture side, I want to decide whether it's a uniform composition or whether it's not. So can I see individual parts? Can I easily physically separate the parts from one another? If I could see different parts inside the mixture, then it's a heterogeneous mixture. And you'll recognize the prefix here, hetero, right? If I'm a heterosexual, my sexual preference is for the other. So this contains other parts, different parts. So examples of heterogeneous mixtures would be things like gravel. It's got different particles of different sizes. I can easily physically separate them from one another. If I had some OJ, orange juice, with pulp, that would count as a heterogeneous mixture as well. If my mixture is not heterogeneous, then it is homogeneous. And just like the prefix as we use it with respect to sexuality, if I am a homosexual, then my sexual preference is for those which are the same as me. And so here, this prefix is telling us that the mixture has particles that appear, at least on the outside, to be the same. So it's a uniform composition. I can't see the different parts, and I can't easily separate them. So something like salt water would fit into this category because I know there are different parts. I've got water molecules, and I've got salt, sodium chloride, and calcium chloride, probably other salts too if it's coming from the ocean. But I can't easily separate them from each other. They appear to be the same. They're homogeneous. If I have something like orange juice without pulp, so I've got that nice orange juice from concentrate, comes in a can, right? It's got no pulp in it. It's nice and smooth. You can see through it. That would be a homogeneous mixture. So the ones that we are going to care about in this section here are the homogeneous mixtures, because these guys are otherwise known as solutions. And these are what we're going to learn about in this section here. So the mixtures which have multiple parts, but they appear to all be one. So solutions are homogeneous mixtures. They're made up of two parts. One of them is the solute, the other one is the solvent. And we can remember these because the solute is dissolved in the solvent. So if I have an example of some sugar water, the substance which is greater in the larger amount, the thing that does the dissolving, is the water. So that's the solvent. And the sugar is dissolved in the water, so that's the solute. And water is a very popular solvent because it's a good solvent. We sometimes call it the universal solvent. And we use it to dissolve things all the time. So things which are dissolved in water are called aqueous, where water is the solvent. And to say aqueous means in water. So instead of saying sugar water, I could say aqueous sugar. And I would know that that means that it's sugar dissolved in water. But water is not the only solvent that can be. We can have nonpolar solvents too, which you'll remember are useful for dissolving nonpolar solutes. So I can, if I want to get out an oil stain, I can use a nonpolar solvent like gasoline. I can dissolve the oil in the gasoline. If an old mechanic's trick would be if you have really oily or greasy parts, you can stick them in a container of gasoline and it will do a good job of stripping away the oils because they dissolve well. So the gasoline here is the solvent and the oil is the solute. Both of these examples had two liquids though. They don't have to be liquids. So in the air is a solution, even though they're all gases, right? They're evenly mixed. I can't easily separate them from each other. The main component of air is nitrogen. And the second most major component is oxygen. And so you can think of air as a solution of oxygen dissolved in nitrogen. It's about 20% oxygen dissolved in about 78% nitrogen. And there are some other components in there too. So which one of them is the solvent? Well, it's the nitrogen. And then the oxygen is the solute. And they don't have to be gases either. You can have a solution which contains two solids if they're evenly mixed. So an example here would be brass. Brass is a solution made of different metals. They're mixed together when they're liquid, and then they're allowed to solidify. It's made mostly of copper. And there are minor components here, which would be other metals like zinc, or like tin, or sometimes lead. Might be components of the brass. And so then these would be considered the zinc, tin, or lead. Those would be considered solutes. And the copper would be solvent. Solutions can either be electrolytes, which are able to conduct electricity, and they can do that because they contain ions. We'll talk a bit more about that in our next lesson. Or they can be non-electrolytes, which don't conduct electricity, and they don't contain ions. And so in general, non-electrolytes will be molecular solutions, because when they come apart, when they dissolve, they don't form ions, and electrolytes are going to be ionic solutions. Because when they dissolve, they dissociate into their individual ions. And we'll talk about that more in our next lesson. We can also test the acidity of a solution. Solutions can be acidic, they can be basic, they can be neutral, and based on their chemical properties, and we can test that with a reaction with litmus paper or with other indicators. And we'll talk a bit more about that a little bit later on as well. Heterogeneous mixtures, right, as opposed to homo. Hetero meaning other parts that are visible, contain undissolved particles. They're opaque, right, meaning that they are not clear. You can't see through them. So examples here, some that we've said already, orange juice with pulp would be an example. Milk is a heterogeneous mixture, right? It's opaque, and that's because even though it seems at the large scale like it is clear, it's got fat droplets. Teeny tiny fat droplets in it that are not fully dissolved because the fats are nonpolar. They don't dissolve very well in the polar water, and that's why it would be considered a heterogeneous mixture.